Okay, so here's the continuation of our discussion. So earlier we have paths that use every edge of a graph exactly once. But this time, let's discuss paths that visit each vertex once, regardless of whether all edges are used or not. So requirement is all you need to do is to visit each vertex once, regardless if you will visit all the edges or not. Okay, so it is called as the Hamiltonian path and Hamiltonian circuit. So it's a walk in the graph that contains all vertices of the graph such that no vertices are repeated. While circuits, of course, it starts and ends at the same vertex that visit each vertex exactly once, except of course for the endpoint. Here in our circuit, you will visit that starting point twice, since that is also the endpoint of the circuit. Okay, so now let's have a uh, situation wherein we'll have the concept of Hamiltonian circuits and the weighted graphs. Hamiltonian circuit is a path that uses each vertex of a graph exactly once, and graph is contains a Hamiltonian circuit is called Hamiltonian. Okay, and later, instead of having edges as lines, this time we're going to have edges with weights. Okay, the lines has its own weight. Okay, so later we'll have different examples for that. Okay, for weighted graphs again, we're going to have a value for each edge. Okay, so let's have an example first. Okay, so the graph below shows the available flights of a popular airline. An edge between two vertices in the graph means that the airline has direct flights between the two corresponding cities. Okay, so let's try to identify whether it has an Hamiltonian circuit or not. Okay, so we have here Portland, Boise, Butte, Salt Lake City, Reno, and Sacramento. Okay, so as you can see here, actually it has an Hamiltonian circuit. Okay, once you start with the Portland, you go to Boise, then to Butte, Salt Lake City, Reno, Sacramento, then you end up with Portland. So as you notice here, we've visited each vertex once, except for the starting point. Okay, and take note, we don't need to visit all the edges. All we need to do is to visit each vertex once. Okay, so you can start with Portland, with the Boise, with the Butte, or Salt Lake City, Reno, Sacramento. So as you notice here, as you can see, we have an Hamiltonian circuit. Another example. A large law firm has offices in 7 major cities. The firm has overnight documents deliveries scheduled every day between certain offices. In the graph below, let's try to have edge between vertices that indicates that there is delivery services between the corresponding offices. Okay, so here, let's try to identify if there's a Hamiltonian circuit or not. So we have San Francisco, New York, Boston, Atlanta, Dallas, Phoenix, Los Angeles. Okay, so in this case, actually there is an Euler circuit here. Hamiltonian circuit rather. Okay, so let's start with LA, going to New York, Boston, Atlanta, Dallas, Phoenix, San Francisco, then you end up with LA. Okay, so as you can see here, we just need to identify whether it has an Hamiltonian circuit or not by looking at this. But actually, there are supporting theorems such as the Dirac's theorem, but it's not that consistent to all the graphs. So therefore, we can just identify it. We can just observe with our graph for us to identify if there's a Hamiltonian circuit or not. Okay, but we're not going to focus to that. Okay, we're not going to focus to that because we're going to have its application. Okay, so again, earlier we discussed about the weighted graphs. A weighted graph is a graph that in which each edge is associated with a value, okay, called as the weight. So remember, okay, each edge has a weight, as a value. Okay, but it does not correspond to the length of the edge and its value. So meaning it's not into scale. Sometimes it's not into scale. Okay, for instance, in the table below lists the distances in miles between 6 popular cities that a particular airline flies to. Suppose a traveler would like to start in Chicago, visited the other 5 cities to this airline flies to, and return to Chicago. Okay, so let's try to find different routes that the traveler could follow and find the total distance flown for each route. Okay, so as you notice here, we have this table and we can have its graph, but take note, each edge has a weight, has a value. For instance, we have from Chicago to New York, that's 713. Okay, Chicago to Washington DC, that's 597. To Philadelphia, 665. To Atlanta, that is 585, and to Dallas, that's 803. Okay, so you're going to identify. Okay, we can graph it first. Let's graph it first, then let's try to identify different routes. Okay, so as you can see here, all we need to do is to just visit all the cities. Okay, it's like a Hamiltonian circuit. It's a Hamiltonian circuit. Okay, here's the graph. Okay, I'll give you the graph of that table. Okay, so earlier, let's say we have from Chicago to New York, the 713 miles. Chicago to Washington DC, that is 597. Chicago to Philly, that's 665. To Atlanta, that's 585, and to Dallas, that's 803. Then, as you notice, New York to DC, there's no flight there. There's no direct flight. Okay, so there's no connection, there's no value. Okay? So try. I'll give you an example. Then you try to identify your own route. Okay. For instance, we have Chicago to New York to Dallas, Philadelphia, Atlanta to DC, then to Chicago. Okay. So all we need to do is to add the value or the weight. You have 713 miles plus 1374, 1299, 670, 544, 597, and the total of that is 5,197 miles. Okay, and then you try to identify. Okay, you try to identify. You start with Chicago, then you visit each city once, and then you go back to Chicago. And you can pause, but I'll present another 2 routes here. And we have Chicago to Philadelphia, Dallas to DC to Atlanta to New York, then going back to Chicago. Okay, and then if we're going to add that, that's 665 plus 1299 plus 1185 plus 544 plus 748 plus 713, and the total of that is 5,154. Then last one, Chicago to DC, Dallas, New York, Atlanta, Philadelphia, then Chicago. And the total of that is 5,239. Okay, you can explore, you can identify other routes here. Okay, you can pause so that you can identify. Okay, and you can have its total weight or the total distance. Okay. Now, for us to filter the routes that we're going to have an algorithm. Okay, we're going to have 2 algorithms, the greedy algorithm and the edge picking algorithm. So, for us to have one route to follow. Okay, so note that algorithms apply only to complete graphs. Okay, it's only applicable to complete graphs. Okay, so let's start first with the greedy algorithm. So the greedy algorithm, we have 3 steps to follow. So we need to choose a vertex to start at, then travel along the connected edge that has the smallest weight. If 2 or more edges have the same weight, pick any one. After arriving at the next vertex, travel along the edge of smallest weight that connects to a vertex not yet visited. Continue this process until you have visited all the vertices. And then, of course, at the end, since this is a Hamiltonian circuit, you need to return to the starting vertex. You need to return to the starting vertex. For instance, again, you can choose any vertex unless there's an instruction like this. You can start with vertex A, you can start with vertex B, C, D, E, or to vertex F. But here, for instance, there's an instruction you need to start at vertex A, so let's start with vertex A. Okay, so for vertex A, we need to look at the connections, the weights for each edges connected to vertex A. So we have A going to F, that's 13. A going to E, that's 5. A going to D, that's 4. A going to C, that's 15. And then A going to B is 8. So of course, we're going to look at the smallest. We're going to pick the smallest weight. And the smallest weight here is A going to D. So that's 4. That is 4. Okay? Next one. After this, we'll have to identify again another route going to from D going to another vertex. Okay, so let's say D going to E, that's 8. D going to F, that's 7. D going to B, that's 2. And then D going to C, that's 12. Of course, we're going to pick D going to B. Okay, the weight of that is only 2. Okay, then for the next one, we have for B. B going to F, that's 5. B going to E, that's 11. B going to C, that's 6. And of course, we're going to pick that 5 since it's the lowest. B going to F. Okay, so that's 5. Then we only have two vertices left, going to E and going to C. If we're going to E, that's 10. If we're going to C, that's 14. So of course, we're going to with 10. Okay, so F going to E, that's 10. Then 10, of course, the last one here is the vertex C. So all you need to do is to go to vertex E, that's 6. Then for the last one, you need to go back to vertex A. Okay, and that's 15. Okay, that is 15. So if we're going to add that, we have 4 plus 2 plus 5 plus 10 plus 6 plus 15, and the total of that is 42. Okay, that is 42. Let's have another example. Let's try to with vertex B. If we're going to start with vertex B again, B going to A, B going to F, going to E, going to D, and then going to C. Of course, we're going to pick B going to D since it has only 2. Okay, weight of 2. So B going to D, that's 2. Then from B, you need to go to E, F, A, or to C. Okay, so in this case, we have going to A since it's only 4, right? Since it's only 4. Then next one, from A going to F to E or to C. So A going to F, that's 13. A going to E, that's 5. A going to C, that's 15. Of course, we're going to pick E, right? We're going to pick E. And since it has a weight of 5. Then we only have 2 choices. Going to F, that's 10. E going to F, that's 10. And then E going to C, that's 6. Of course, we're going to C with a weight of 6. Then last one, of course, we're going to, no choice, we have going to F. Okay, so that's 14. And then, of course, you will go back to vertex B. Okay, and that is 5. So all we need to do is to add that 2 plus 4 plus 5 plus 6 plus 14 plus 5, and the total of that is 36. Okay, that is 36. So as you can see here, you can try. Okay, you can try with the other vertices. You can start with vertex C, vertex D, vertex E, or vertex F. Okay, then try to compare which of the following routes has the smallest weight. Okay, have a smallest weight. Okay. Let's have another graph. Here you can pause the video, then you can try to identify the Hamiltonian circuit here. Okay, you can use your pencil and pen and paper to try and identify the Hamiltonian circuit using the Grady algorithm. Okay, so in this case, we're going to start with vertex A. So A going to D, so that's 5. Then going to C, that's 4. Going to B, that's 3. Going to E, that's 5. And then go back to A, that's 9. So if we're going to add that, that is 26. Okay, so again, your A going to D, of course, that is the lowest. That's only 5. Compared to A going to E, that's 9. A going to C, that's 6. And A going to B, that's 8. Okay, so then you're going to follow that from D. Then you compare D going to E, that's 8. Going to B, that's 5. Then going to C, that's 4. Since 4 is the lowest, you're going to C. And repeat the process until you get the greedy algorithm. Okay, the Hamiltonian circuit using the greedy algorithm. Now, let's have this situation. Dora needs to mail a package at the post office, pick up several items at the grocery store, return a rented video, and deposit at her bank. So uh, she has different errands for this day. So we need to identify. Okay, we need to identify its driving time, where she can maximize her time. Okay, or minimize the time of her driving. So the estimated driving time in minutes between each of these locations is given in the table below. Okay, so as you can see here, we have from home going to post office, that's 14 minutes. Home going to grocery store, that's 12 minutes. Home to video rental store, that's 20 minutes. And then home to bank, that is 23 minutes. And then we have from post office to home, that's 14. Grocery to post office to grocery store, that's 8 minutes. Post office to video rental store, that's 12 minutes. Then post office to bank, that's 21 minutes. Okay, then from this table, let's try to create a graph. Okay, let's try to create a graph based on this. So we'll have this. Okay, so we have the greedy algorithm approach with this graph. Let's start at vertex home. So from home, starting that, from home, going to post office, that's 14 minutes. Going to grocery store, that's 12 minutes. Home to video rental store, that's 20 minutes. And home to bank, that's 23 minutes. Of course, we're going to pick home to grocery store because it only has a 12-minute driving time. Okay, then from that, let's compare. So grocery store to post office, that's only 8 minutes. Grocery store to bank, that's 11 minutes. And then grocery store to video rental, that's 70 minutes. Of course, we're going to pick the grocery store to post office, that's 8 minutes. Then for the next one, from post office going to bank or to video rental. So if we're going to bank, that's 21 minutes. Then from post office to video rental, that's 12 minutes. Of course, we're going to pick the video rental. So that's 12 minutes. Then no choice, before going to home, you need to visit the bank, that's 18 minutes. And then from bank, you need to go home, that's 23 minutes. Okay, so if we're going to add that, so that's 12 plus 8 plus 12 plus 18 plus 23, that is 73 minutes. And that is 73 minutes. Another approach. Okay, we have another algorithm to follow. We have the edge picking algorithm, wherein we have again 3 steps to follow. The first step is we need to mark the edge of the smallest weight in the graph. If 2 or more edges have the same weight, pick any one. Okay, for number 2, we need to mark the edge of the next smallest weight in the graph as long as it does not complete a circuit and does not add a third marked edge to a single vertex. We need to continue this process until we can no longer mark any edges, then mark the final edge that completes the Hamiltonian circuit. So take note, there's consideration here as long as it does not complete a circuit, so we need to pick different edges. It's not necessary for us to have the continuous root. Okay, we can have the root after we pick all the necessary edges. So it does not complete a graph and does not add a third marked edge. So take note, it has only 2 marked edge for every vertex. There should not have a third mark edge for every vertex. Okay? Maximum of 2. For instance, earlier we have this graph. let's try to use the edge picking algorithm. So again, look at all the edges and its weight, and then let's compare and identify the smallest. Let's identify the smallest weight. So in this case, we have B going to D. Okay, so our edge BD, so that's 2. So let's get that. Then from that, let's identify, we have from 2 smallest, that's 4. Next is 4. So in this case, we have AD. Okay, edge AD or DA, so that's 4. And then after 4, we have 5. Okay, it's either we have edge EA or AE and edge BF or FB. Okay, if we're going to pick AE, there will be no problem since A will have 2 connections or 2 edges. That's okay. And then if we're going to pick BF or FB, it's okay also since B will have 2 connections only or 2 edges only. Okay, so let's pick both the BF or FB and AE or EA. Okay. Then the next one, there's no closed circuit yet, and then also there's no 3 connections or 3 edges for each vertex, so we're okay. The next one, we have 6. Okay, we have EC. If we're going to pick EC, there's no problem with that since E will have 2 edges. So let's pick that EC or CE. But if we're going to pick BC, which is 6, if we're going to pick BC, there will be a problem since B will have 3 connections. Right? There will be 3 connections for B, vertex B. Okay? So in this case, let's skip the vertex BC. Then for number 7, so we have 6, we have 7. Then if we're going to pick 7, there will be 3 connections or 3 edges for D. So let's skip that. For 8 also, there will be 3 connections for D and E. Same goes here with AB or BA. There will be 3 connections. So we're going to skip 8. 9, there's no 9. How about 10? So 10, there will be 3 connections, 3 edges for E. So let's skip that. 11, also. So 3 connections or 3 edges for B and E. So let's skip that. Then for 12, 3 connections for D. Right? There will be 3 connections for D. So let's skip that. And then, how about 13? Okay, for 13, we'll have AF, but there will be 3 connections for A, so we'll skip the 13. Then for 14, I think there's no problem with 14. Okay, with CF or FC, since vertex F and vertex C will have 2 connections or 2 edges. So that's okay. Then for 15, last one, there will be 3 connections for A, so let's skip that. So as you notice here, we have now the edges that we needed. Okay, so let's try to create our Hamiltonian circuit. So we can start with A, end up with A, start with B, end up with B, start with C, D, E, or F. Okay, let's say we start with A. So A going to D, going to B, going to F, going to C, E, then we go back to A. So the total of that is 36. Okay, and then also if we're going to reverse it, let's start with A going to E, then going to C, going to F, B, D, A. The result is the same. The total of that is 36. Okay, and also if you're going to start with B, going to start with C, D, E, and F, the weight of that is still 36. Okay, the weight of that is still 36. Okay, you try this one. Okay, try this graph. Identify all the edges with smallest weight. Then try to identify the Hamiltonian circuit using the edge picking algorithm. Okay, so you can pause the video, get your pen and paper to identify the Hamiltonian circuit here. Okay, so let's try to reveal the answer. So of course we're going to start with the smallest weight, which is 3. Okay, that is BC. Okay, so that, or CB, HBC or CB, that's 3. Then for next one we have 4. So we'll have vertex or edge DC or CD with a weight of 4. Then for next 5 we have 3 choices. It's either DB, DA, EB. But here, if you are going to pick DB, look at this. If you're going to pick DB, there will be a closed path. So there will be a circuit already. So we need to skip BD. Okay, we need to skip BD. But if we're going to pick AD and BE, I think there's no problem with that. Okay, because there will be 2 connections only for D and then 2 connections for B. So there's no problem with that. Then from this, we'll have 5, then 6. AC or CA, skip, since there will be 3 connections for C. 7, skip again, there will be 3 connections for C. We have 8, 3 connections for B. So skip this one, and then also this one, there will be 3 connections with D. So we're going to pick 9. Okay, let's pick 9 or AE. Okay, then from this, you can now identify the Hamiltonian circuit. You can start with A, B, C, D, or E. But in this case, let's say we start with A, going to C, D, going to C, going to B, E, and then A. Then let's add that, and the total of that is 26. Actually, it has the same root from the greedy algorithm, right? So you can start with A going to D, C, B, E, or A, or in reverse. You'll have the same weight. You'll have the same weight. Okay? Then earlier we have the situation about running an errand, running errands. So let's try to use the edge picking algorithm here. So take note, you don't need to start at home yet. All you need to do is to identify the smallest weight up until the largest. Okay? Then after that, you're going to create the Hamiltonian circuit with starting vertex of home. Okay, but take note, first step, you don't need to start at home in edge picking. Okay, so in this case, we'll have 8, of course, post office to grocery store. So let's get that. So that's 8. Then from 8, we have 9, 10, no, 11. So 11, grocery store to bank, that's 11. Okay, then we'll have 12. If we're going to pick home to grocery store, there will be 3 connections for grocery store, so we need to skip that. Then post office to video rental store, I think that's okay, so that's 12. Let's get that. Okay, then after 12, we have 14. But in 14, we'll have 3 connections for the post office, so we need to skip that 14. Then for 17 also, there will be 3 connections for grocery store, so we need to skip that. 18, look at this, when it comes to 18, there will be a closed circuit already, there will be closed path already. So let's just skip this one. Though there's only 2 connections for bank and video rental, still you don't have connection to home. So we need to skip that 18. Okay, then next one is 20. And in 20, we have 2 connections for video rental store, so that's okay. The next one, we have 21. So in 21, post office to bank. So there will be 3 connections for post office, so we need to skip that. Then last one, 23. So we have bank to home. So there will be 2 connections only for bank and to home. So of course, we're going to pick that. So now, after this, since we're done now with picking edges, right now we're going to have the Hamiltonian circuit. Okay, starting at home and then we end up at home. So here we can start with home, going to bank, going to grocery store, to post office, video rental, then you end up with home. Or you can have home to video rental store, to post office, to grocery store, to bank, and then going to home. It's the same because the total weight of that, or the total minutes for that, is 74. Okay, there will be 74 minutes driving time in using edge picking algorithm. So if we're going to compare the two, the edge picking algorithm and the greedy algorithm, it's much more efficient when it comes to greedy algorithm. Okay, but it's not all the time. Okay, take note, it's not all the time that greedy algorithm is better than the edge picking. Sometimes it's in edge picking is better than the greedy algorithm, or they could be the same weight. Okay, so that's it for the Hamiltonian circuit and Hamiltonian path.